In 1839, the first black and white image was taken. This marked the advent of humankind's ability to document life. However, color photography was not invented until 1935. In between these two timestamps of human history, millions of black and white images were captured. But how do we colorize them? Real quick before this video starts, I just wanted to let you guys know that only 0.1% of my viewers are subscribed, which only equates to about 200 people, and my goal is 1,000 people by the end of the year, so if anyone watching this video could subscribe, that would be a huge help. Alright, on to the video. Black and white film was originally painted by hand, and later in the digital age, the individual pixels were painted. This was very painstaking and often involved a lot of human labor. So people had to come up with a new way of colorizing black and white images. We'll be designing a deep learning neural network that can take in the black and white images and output the colored channels. But the keen among you might ask, how are we going to extract any data from the black and white image that can be used to create a colored channel of the image? A simple method could be to take the black and white image, transform it into an array of values, each ranged between 0 and 255, and then put each pixel into a layer of our neural network. But there's a problem. If we were using a 256 by 256 black and white image, that would require 65,000 input nodes to our neural network. If we were using a 3-layer neural network with the first layer having 128 nodes, the second layer having 64 nodes, and the third layer having 32 nodes, that would end up requiring more parameters than most large language models. When a human sees something, the view is relayed back to the primary visual cortex at the back of the human brain. Here, key visuals such as edges, color, and orientation are extracted from the input image. We can just steal from nature in this case and use a tool that's already been developed called a convolutional neural network. By convolving an ordinary image with a convolutional kernel, we can extract specific features from the image, such as edges, color, or orientation. Furthermore, we can use an encoder-decoder architecture, also known as a unit, to decode our information into an encoded representation that can then be decoded by a separate part of the model. This may sound difficult, but in reality, this model can be implemented in just a short few lines of code. However, some keen among you might be curious as to why the output of this model only contains 2 channels, rather than the predefined RGB 3 channels. However, to understand why I did this, you have to understand one of the worst parts about AI image colorization, aka color spaces. For each pixel on your computer screen, there are 3 red, blue, and green colors that your brain simply combines to form one color. You can change the color by changing the amount of light coming through the red, blue, or green pixels. Although RGB is the most popular color space, there are probably hundreds of other color spaces. But the most important one for us is going to be one called the lab color space, standing for lightness, A channel, and B channel. For our project, we can just use the L or lightness channel and allow the neural network to predict the A and B channels, thus reducing the number of outputs by 1. So how did this happen? Well, an aspect of neural networks that I haven't covered yet is called the loss function. In my code, it was as simple as implementing one of PyTorch's built-in loss functions, known as binary cross entropy. Although the mathematical equation for this actual loss function looks pretty complex, in reality all it does is just measure the difference between the predicted and ground truth values. Unfortunately, due to the simplicity of the loss function, it's also pretty easy to exploit, and here all our model did was choose the dullest colors, which produced the minimum difference. And unfortunately, this is probably going to happen with any loss function we use, since they all end up resorting to the lowest and dullest colors to produce the minimum difference. So how are we going to solve this problem? What kind of neural network could we use to produce vibrant colors that also match the image that we've input in? CGAN is short for Conditional Generative Adversarial Network. It consists of a generator which produces colored images based on black and white inputs, which then get mixed in with real colored images. The discriminator model then picks out which images are real and which ones are fake. The generator's job is to fool the discriminator and make images that are as realistic as the real ones. The best part is that they don't rely on loss functions, which means we can make crisp and vibrant images that aren't reliant on any extra minimizing or dull colors. Conditional GANs are much harder to implement, as you can see with these lines of code being much longer than the original convolutional neural network. After about 100,000 training steps, I managed to get some pretty good results, which I'll show you in this short slideshow. Although the results are much better than what I was originally getting with my convolutional neural network, there are still a few things to be desired. Some examples are there's this weird blob of color in a lot of the images, as well as occasionally when there are rare objects, the AI does not know what to color them. Although there are several optimizations I could make in my code to get the colorizations to be more accurate, I just don't have enough time to go into any of them, so I'm just going to leave my project the way it is. I hope you enjoyed, and I hope you consider subscribing after seeing this.